Okay, I would like to explain some changes I've made to the model and to the code. Let me go first to the document. I changed the name here, Info Flow Patterns in Sensor Networks. I also changed some notation to make it agree with the general model. I'll have to run the bibtex, but you can see here I'll have to run the bibtex. I changed the rings to be R. I changed the unknowns to be X. I changed the power transmission matrix to be T. And I changed the power capacity to be C. The information in each ring is A. So I did not include compression yet, but I will put that in later. Oh, sorry, I missed one here. This C should be an X. Let me change that now. All right, so this makes this more in agreement with the notation that I use in the next document. Okay. So let me go back to the code. So I made that also some changes in this code. I included the information vector, compression vector, but I have not used this yet. And then this is the power capacity vector. Okay. And I call these I can say rings, but I can also say nodes, because this same model will work for a more general case where you don't have rings and sectors, but you have different subregions that pass information to each other. You will see later that the hexagon model also can use this model. I added this transmission power exponent, gamma, because here we used gamma as 2. Sorry. Here we use gamma as 2 for the transmission energy, and I changed it to be general. All right. So that will make this model more general. All right. I added some plots. In this section, I also computed the power matrix because we need that later for the plots. And down here we have several plots. You can see them over here. I plot for, this is the information flow, so we had that before. This is, let's see, this down here. This one is power flow, stepwise power flow and direct power flow. You can see most of the power flow is direct. The total power flow is linear, and this is because in the ring model, you have more and more sensors for the higher and higher rings. You see? There are more sensors out here than in here. Right. So since there are more sensors, there's more power capacity. That's one of the weaknesses of this model. Right. This is the percentage power flow. This is the percentage of capacity. So you can see that the direct power flow uses most of the power capacity. These markings are not good. I would like to make these to be integers. Maybe you can help me with this. But this is the ring index. It should not have 2.5. There is no ring 2.5. There's only 1, 2, 3, 4, etc. All right, I think that's the last one. And then this was the total power consumption. We don't really need this one because this the same is here. I think I will just remove it now because it's not necessary. I'll just remove this. Okay. Now, the next thing I mentioned was that I would like you to make a figure that shows the situation for each node. So I have that here. I'm not sure I want to keep this notation. Here I put F, and F really is X. So maybe we can change this notation. You can help me change this notation. So here we have several nodes. You start with node 0, node 1, node 2, node 3, and so on. All right. So let's replace these. Let's replace these F's. This one is actually the information flow from 1 to 0. So I'm not sure if it's X, I think it's X01 because it's information flow from 0 to 1, from 1 to 0. Then this would be X12, X23. This one here goes from X, this is X. Well, it's really not necessary to have two indices. So I'm not sure what to do with this. I think maybe we can keep as F for now because the F has one index, and then this, what does Fj means is equal to the stepwise flow from a node j to node j minus 1. It's the stepwise flow from node j to node j minus 1. So there is stepwise flow. And then you also have this direct flow. So there should be an arrow like this, an arrow like this. I don't know how you want to do this, but all of these have arrows that show direct flow. So my picture is not good, but I think maybe you can make a better picture. All right, so we want to show this. Now it's important to realize that this picture comes from the result that we simulated here. The result here shows that there is stepwise indirect. We didn't know that, and we didn't assume that. We found out from the simulation that there is stepwise flow and direct flow. If we know this, then we can solve for these values exactly. All right, so this is one picture. Okay. All right. That's one picture that you can create. Then for the single node, you can make two pictures. There's a picture for information, and then there's a picture for capacity. And then there's a picture for power, sorry. So both of these I think are important. So this is for a single node. For node n, I have information in, which is Fn plus 1. I have the information at node n, which is An. And then I have the information that's going out, which is Bn times An plus Fn plus 1. Because the information here is Fn plus 1 and An, but then we have compression. All right, so the information out is Bn times An plus Fn plus 1. This information out splits into two parts. There's the stepwise flow, and then there is the direct flow. Now, from this picture, we can see that the direct flow has this form. Part of the information goes this way, that's Fn. The remainder goes direct flow. So I get this quantity, which is the total information, and subtract the direct flow information. Okay, so this is the information picture. Now I have the power picture. From node N, I have power capacity Cn. Now here I have the power that goes for direct flow is the information times n to the gamma. The n to the gamma is here because when the power goes directly to the source, the distance is n, so the power for each unit of information is n to the gamma. And this is the number of units of information. All right, so this one is stepwise power, which is Fn. Because this is only traveling a distance of 1. So the power is Fn. I could say Fn times 1 to the gamma, but 1 to the gamma is 1. Okay, so stepwise power is Fn, and then the power that goes directly to the source, the direct power, is this quantity here. And we're going to use these facts to solve for the theoretical solution of the system. And I would also like you to write that into the document if you can. So we'll look at that next. So here we have a review of what we just talked about. The information that goes into node K is Fk plus 1. The information that goes out is Bk, the compression, times Fk plus 1 plus Ak. So this is just like what we saw in the picture. Right? The information that's passed directly from node K to node K minus 1 is Fk. The information passed from node K directly to node 0 is the information that comes in plus the information that's at the node, and subtract the information that goes to the next node. Okay. So this information goes directly to the source. The sum of these two informations is this information here. We also have the power. I have the power from the stepwise transmission that goes from K to K minus 1. That's Fk. And then I also have the power that for the information that goes directly to node 0, which is this term here. All right. So this is the same thing. In the previous figure, I used n instead of k, but everything else is the same. Now we found that when we have the best power consumption, we had equal proportional power consumption of all the nodes. Okay. We saw that from the spider. The spider here shows that if I take the power as a percentage of the capacity, then this is the power for stepwise, this is the power for the direct to the source node. The total percent power is constant for all of the nodes, or here we say rings. Ring and node mean the same thing. Constant power. So I use this fact to solve for these quantities F. All I need to solve for are the quantities F, because if I solve for the information flow F, then I can find the information flow to the node, to node 0, to the direct information flow, and I can also find the power consumption. So these F represent stepwise information flow. Okay. So that's the optimization problem. I equalize the proportionate power consumption of nodes. Let Z denote the proportionate rate of consumption of all nodes, so that CKZ is the actual power consumption of each node. Now, in this document, I used Z, but I think that P is better. P is what we used in the LaTeX document. This P here. Notice this P is here, and here the C is under in the denominator. But the equation is the same. So when you write this in LaTeX, please replace the z with a p. Now, using this information, we may write power balance equations for each node based on the diagrams above. The diagrams above, I mean this diagram here. I see now I made a mistake here. Here, the information that's sent here is Bn times An plus Fn plus 1, but I have to subtract the information that goes this way. The information that goes stepwise is Fn. Okay? Actually, this n should be the same like this. And the information that goes to direct is Bn An plus Fn, An plus Fn plus 1 minus Fn. And that's not inside. And then this is all times n to the gamma. So just to notice here, you have an equation that looks like this. You have Bn An plus Fn plus 1 minus Fn times n to the gamma plus Fn is equal to Cn, and then here we're using so it's going to be so this is the total power. Now, what we want this to be is equal to Cn, and as I said in the document here, I have Cnz. So let me rearrange. First of all, let's get the Fn terms. Here I have Fn times 1 minus n to the gamma. Okay? Then I have Fn plus 1, and that becomes, here I have beta n to the gamma. Okay? And I'll bring this to the other side. I have minus Cnz. And what's left over is this term, Bn An. Okay? So you see this form of equation here. This is exactly the equation that we have here. Okay? That's exactly what I have here. Here I have n equal 2, n equal 3. If you look back at this equation, you will see this is the same equation as this one. So I can write this equation for all of the nodes. And then I rewrite this as a matrix. Here's the matrix. These are the diagonal entries. This is the sub-diagonal. And here is the last column. I multiply this matrix times this vector. This last entry is Z. This one is F. I believe it's Fn. Okay. And then here's my result. Okay, again, this matches exactly with these equations I express in matrix format. So you can put this matrix into the paper. This is also all zeros here. Now I can simplify these equations. I define a new unknown, pk, as ck over bk times k to the minus gamma. And minus qk as 1 minus k to the gamma over k to the gamma bk. What I'm doing is I'm dividing each row by k to the gamma bk. If I do that, then the diagonal entries become 1. That makes it simple. These entries down here become minus qk. Sorry, these become minus qk. And then I bring this last column over to the other side, and I combine it with this one. So that's how I get WK is equal to the PKZ minus AK. Okay, so here's a simple form of the equations. And these can be solved for F2 up to Fn. We solve them one by one like this. We solve them in terms of W. Now W, what does W involve? W involves PKZ minus AK. PK is known, AK is known, Z is not known. Okay? So I can rewrite these equations in terms of Z, P's, and the Q's. The P's are known, the Q's are known, the A's are known. Only Z is not known. Then there's one more power equation for the very last node. Using these two equations, I can find Z, because I can set this equal to this. Now, to simplify the expression of these equations, I can define a vector I call P and a vector I call Q. And then I also define the entry of capital Q is defined in terms of the small q. We define Q up here. Q is defined up here, you see? And then capital Q is the product of the small q. Okay, so we have P, I have Q. This A is the information for each node. Then I can replace the unknowns up here with these unknowns. These here. This ZP is the same as, the ZP times Q is the same as this. This minus A times Q is the same as this. So this is a simpler way of writing this long expression. Okay. That gives me a solution for Z. I solve this equation for Z. I have a term Z here, I have a term Z here. I can bring them together. Now I can also define Qm this way. And this enables me to find all of the information flow from each node. But the important quantity here is Z, because this is telling me how much power is used by the network. So here's another way to express Z. Okay, so I think down to here, if you can write these equations into the LaTeX document, that will be very helpful. And I hope as you write these things, you will get some more understanding. Okay.